After an hour and a half, the techniques that I've incorporated into this miniature course will allow the concepts to sink in better for you all. I've been helping customers over the years who don't know how to size functionally, helping them get started, and been taking notes. And hopefully all the notes I've taken on how people really do learn this better will be useful for you all. So without further ado, I'm going to jump in. Sizing methods. There are a bunch of ways to size software. You can use lines, you can use functions, and then there are the other methods out there now, particularly with the advent of agile life cycles and the need for storyboards to have some sort of size associated with them. You now have use case points, a t-shirt sizing, story points. But as you can see under functions, I'm showing all the ISO certified functional sizing metrics in addition to our own Gallup function-based sizing. There are a bunch of ways to size functionally, the oldest being IFPUGs, function points, which go back to the late 70s, and the newest probably being full function points. Function-based sizing, what Gallup has in CRSM, is fully compatible with function points. And so for that reason, and for a variety of others, this presentation is going to focus on function points. I'm going to try to keep this humorous. It's an hour and a half long, and I'd put you to sleep if I didn't. I'm going to start out with this slide here. What is the advantage of sizing functionally? I know a lot of people, our customers included, come from lines of code world. Our newer customers are increasingly familiar with function points. What is the advantage of functional sizing? Well, I'm going to put this slide, if I had it up, I'm going to let you guess a little bit. Okay, guessing time is over. Functional sizing is intuitive. It actually does correspond to things people need to work with: screens, outputs, inputs, reports, etc. It does correlate with the scope quite well. I could put up a scatter plot like this, and you'd see the correspondence between function points and effort and duration. It's very clear. And finally, there are many adherents to functional sizing. You've got good company if you do learn how to size functionally. It's a very commonly accepted metric. What we're going to teach today, enough to get the job done. I'm not going to give you a week-long course in sizing using function points, but I'm going to hopefully give you enough to actually start sizing. So there's a difference there. And because of that, I've decided to simplify the terminology. I'm not going to use strictly IFPUG terminology. I'm going to use terminology that appeals to, I think, you on a more intuitive level. But you'll immediately, if you're at all familiar with function points, see how things are connected. I'm going to remain fairly close to the standard. What you see here is the IFPUG logo for those who don't recognize it. I've chosen to superimpose my interpretation of what we're teaching today. And so I did actually hint at this in the last slide. We're going to teach function points without what I call the extra baggage. There's a lot of terminology, EIs, EOs, EQs, RETs, FTRs, lots of acronyms. I'm not going to be referring to most of those today. I'm going to be using intuitive terms instead. Now, function points, functional sizing in general, some people start with the idea of an output or an input or an inquiry, data. However, I think the better way to start is by defining a few rules. I think that people get hung up on the separation between function points, on where to start counting, where to stop counting, on what's big, small, little, all those things that are the rules surrounding function point counting. And so we're going to go through those largely first, and we're going to reemphasize the rules as we go. I think that once you have the rules down, the rest falls into place a lot more naturally. First, we're going to start with the application boundary. The application boundary is what defines the external layer of what you're doing. For example, if you've got a screen on a terminal, the application boundary is what the user sees. That's the boundary of the screen, is the glass of the display. And then at the other end, the application boundary may be the other things that the application interacts with. Whatever goes in and out of the application boundary is where you count functions. And most functional sizing metrics work that way. You have to enter or exit the application boundary. If there's something that's happening purely inside, in most cases, you wouldn't consider that to be a function that's worth counting. The second rule is that if the user doesn't see it, you don't count it. The user actually has to, in traditional functional sizing, put eyes on a feature, and that would constitute a function point, function point. I put a little star there, an asterisk, because there are interpretations of that which violate the user perspective. And I believe that those interpretations are very necessary in order to count functions correctly. And indeed, future sizing metrics such as cosmic are based upon the idea that the user perspective isn't always the full perspective that's required to count functions. And I'll provide examples to illustrate that. But largely, it is a user perspective. If it's user-facing software, transactional software, for example, that involves user input, then it really will be the user perspective. So you don't have to feel that this rule is too often violated. But in general, it's better to keep in mind the application boundary, because that can define multiple applications. And again, I'll get into that. I try to re-emphasize the rule, what we learn here. The next rule that I think is a very important one is that a function exists at the point where the job is finished. Now, what does that mean? Well, we'll go into that, but specifically, if you have a function within a piece of software that's churning along and then it stops and it's waiting for the next thing to happen, the next input from outside, that's where the job is finished. If you have, for example, a dialogue that has a lot of controls on it, but nothing really happens until the user presses OK, that's where you count your function. At the point the user presses OK, all the things necessary along the way until that OK button is pressed. You don't count each control as a function. You count the last thing that leaves the system in an equilibrium state, waiting for more to happen. Here's an example of that. This is a very complicated screen. I'm not going to get into the business of classifying all the things on this screen, but I'm using it to point out what leaves the function in an equilibrium, what leaves the system, I should say, in an equilibrium state. And so you see a box around the output here. I haven't called it an output, it's just a box around this, and you see other red boxes in various places. The key to where these red boxes are placed are that once you display the output, once you click on the update button in this dialog or the refresh button here, once you select the sound here, the system is done. It's waiting for the next thing to happen. If you were to select the mode here or type in a name or do a variety of the things in this dialog, it wouldn't be done. Nothing would be updated. The system would be waiting for you to click update, and then it would do its work, and the system would then be done. Doneness is very important, and that's where functions are defined. In this little box here that shows an input for, in this case, where the application itself is merging multiple audio streams. Once you click these buttons here, the work is done. Until you've actually clicked the button, the work is not done. However, you see that box is very small. That's because very little is required to leave the system waiting for more to happen, for more user input to occur. So sometimes it's a lot of stuff inside a box that's required to make the system then wait for more. Sometimes very little. The functions can be very small or very large. The next rule is that applications process data. Almost all applications process data. Data that sits inside the application or data that's external to the application. But most inputs that the user makes are updating data inside or outside the application. Most outputs that the user sees, user being a person or another system that the application is interacting with, most outputs are deriving information from internal or external data. An inquiry that a user may make is a request to get data. So it's all about data, data in, data out. Data is the currency with which we evaluate functions. I'm going to bring that to life here in this diagram, showing you the application boundary, this box here, this thin line box, and then the arrows going in and out of the application boundary. In this example, we have internal data, which is inside the application, and external data outside the application. An input, and I'm starting to get into classifying functions here, an input sends data inside the application, updates internal data. An output takes data from the application, from inside or outside the application, processes it, and sends it outside the application boundary. An inquiry is a request for data that doesn't do very much with the data. It's simpler. Sends it outside the application boundary. Again, the difference between inquiry and output is an output actually derives new information. It's derived information from the data. An inquiry is much more raw. It doesn't really do much in the way of processing the data. But you see here how these transactional functions are going inside and outside the application boundary, processing or requesting or updating data. And then once that processing, requesting, or updating is complete, we're done. That helps to discriminate the idea of where a function starts and ends. Once the data is output, once the data is input, you're done. If you're in the process of inputting something and it's not up to the point of updating data, you're not done. External data is simply data that lies outside. You're not updating external data. You're just using it for an output. So data and transactions are two different terms that we use in functional accounting. And I've used them already. The red ones, the red items are the transactions moving in and out. And then they work, of course, with the data. This is a common issue that users have. What's an inquiry and what's an output? So here is a stack with data at the bottom, and the red arrows are showing data leaving the application interface. An output type of transaction would perform calculations on either data or simply perform calculations. It doesn't have to access the data, which is a little proviso to what I said before. It usually does access internal data, but it can just perform calculations, and that calculated data is then sent out of the application interface. So there's a little bit of wiggle room in an output. Sometimes it actually is, as I mentioned last slide, processing internal data and sending it out, but it's the processing that's the key. It's performing some derivation that it's sending out. An inquiry is not performing any calculation. It is simply requesting data and sending it out with a minimum of to-do or processing. But this is the difference here between an output and an inquiry. Of course, some functions are bigger than others. There's a function that might have 2 or 3 inputs on it. Say it's an input, and 2 or 3 controls or fields that the user modifies. And then there can be an input that has 50 fields that the user modifies. Same going for output. There can be an output that has very few fields or very many. You don't want to think of them as being the same. Now I'm stopping here to take a breath, and I'm going to go over what we've just discussed. The rules are count only that which enters or exits the application boundary. The application boundary being what the user sees or what the quote-unquote user sees, user quote-unquote being another application. Count whatever is visible from the user perspective. So if something's happening inside the application, almost always it's hidden from function counting. In C or function-based sizing, we recognize the existence of something called an internal function, but it's very rarely used. You have to find a function that's strictly hidden and that's strictly important and to call it a function-based, to call it an internal function. But normally, you count what's visible. The next rule is count only that which leaves the system in an equilibrium state, meaning it's not waiting for the user to click an OK button. The user's clicked that OK button. It's processed. It's waiting again. Maybe if it's another application that is accessing the API of a server application, the API call is made, information is returned, the system is waiting for more information. So it's always that equilibrium state. Over and over again, when counting functions, I've seen people mess that up. They don't consider that it has to be waiting for more, that the data has to be updated, and then it's waiting for more. They'll make the mistake of saying, okay, this bunch of inputs on this screen is a whole bunch of functions. No, no, no. They're just fields that are part of the function. You have to wait until nothing else is happening. And to help you in that idea of the equilibrium state, you look at the persistent data. If an input is touching persistent data, it would be that once that data is updated, that's where the input is done. An inquiry, once it gets that persistent data, it's done. An output, once the processing occurs and it's sent out, that's where it's done. Functions are organized into 2 categories, transactional and data. And finally, they're not all the same size. Okay, we're going to have a whole bunch of examples. The rules are kind of theoretical, even under the best case, but once we start counting, hopefully those rules will start to become much clearer. I'm going to introduce you to the various concepts slowly. I'm not going to give you a full-blown function point count with everything I show you. I'm going to show you various parts of counting, and we'll get more complex in our counting. We'll get more complete as we go along. We're going to work on the basics first. So this is a dialogue. I'm going to show you a lot of dialogues. In this case, the dialogue itself is not one whole input. It turns out that in many modern dialogues, a lot of things are happening on the dialogue. There's a lot of functionality built into them. There's screens that have different things happening. Maybe with this screen, for example, you specify description, analyst, task type, category, etc., all these items here in this red box, and you click OK. That certainly is an input. And a lot of people may think that's the only input. This screen, this dialogue is an input. Well, it so happens that on this dialogue we have a status bar down here, which is not doing much, but it is doing something, and that's an inquiry. We have a help button here. That's an inquiry also. So on this one screen here, we have at least 3 different functions, 2 inquiries and 1 input. In the back of our mind, we know something's being updated, and we have to keep that in mind. Often when counting functions, you have to infer what's being updated. or you have to have that in the documentation somewhere that you can refer to. In this case, we know that the work breakdown structure, which is a data structure, is being modified. I'm thinking of the work breakdown structure as kind of a logical concept. I'm not thinking of it as a physical idea, and that's a very important point that we'll reemphasize. I don't really know where this is stored. I don't really know how many tables the work breakdown structure takes, but I know it all comes together as something called the work breakdown structure, and that's what I want to keep in mind here. As I mentioned, you don't necessarily know about that data structure beforehand. And in much function point counting, you're not provided with that level of detail that maybe comes in at the architectural design level or further, and so data structures are not specified. If you only know the functionality of a piece of software, you're going to have to infer that data. That happens frequently. You're going to have to figure out, oh, there's a work breakdown structure that is relied on, or there's some other sort of logical data source that's relied on. Usually function counts grow over time as an application is more evolved for a few reasons. One is obviously functionality invariably grows. You need to do more, and so the early function count is not necessarily complete. Also, the data is refined more. And that's reflected in function point, what we call expansion factors. You can learn how to grow a functional size over time. That's something that CRSIM has built into it. You can specify a functional size count done at the proposal stage, and we'll automatically add a sizing adjustment for the early stage of that function point count. Whoops. This is another classification example, an inquiry, sorry. This could easily be mistaken as an output, actually. I changed this myself. It looks like an output. It's a report. Why is it an output? Well, it's not an output because it doesn't really derive data. It actually shows these categories from an internal data structure without any modification. I mean, it's pretty. It's got a lot of colors. It's got a pie chart. It uses a component that's probably called an output, but it actually is an inquiry. It's a common mistake that something is an output, which is in fact an inquiry. And one way of intuitively recognizing that is that an output takes more work. If this were an output, it would be a lot more work for the programmer to do than an inquiry. This was a relatively trivial thing to create. And so the idea that it's an inquiry is not far-fetched because it really does show information that was already present in the underlying data structure. What was that underlying data structure? I'm just going to call it the estimate now. And logically, that everything belongs in that estimate. So that's the data that's associated with that. Data is not about where things are stored. Data is how things are logically organized. And we saw that before in the WBS data and then in the estimate data. You're going to see that over and over again. I'm not thinking about things in a physical way. I'm thinking about things in a logical way. All these handbags, for example, are stored according to their colors, I guess, and the line that they're in the designs. And that's a logical way of storing things. Not necessarily physical. Physical, I would have stored all the handbags by, all the pocketbooks by their size, perhaps. Another example. Here, we have an output. Why do we have an output? Because we're actually doing some calculations here. It's a small output. We're again using the estimate data. However, we're processing the estimate data and putting some additional information on the screen, which is not simply an inquiry. Here's another classification example, getting far more complicated here. I think you all recognize the software that I'm counting, iTunes. And you can see that on this one screen, we have a ton of things that are not really part of one massive dialog, but all interacting separately as smaller features. We have an output at the bottom that has some processing to display that. We have inquiries largely at the top that do simple things such as moving the track back and forth, changing the point you are in the track up here. Sorry, I should point to these. The inquiry here is a search. This inquiry here, that's this larger box, is showing the information for the current, in this case, podcast. So there's a lot of things happening here, and they're all broken up into very many inquiries and inputs. This is not by any means a complete function point count. I'm just trying to show you a bunch of things on the screen, but not necessarily all of them. In terms of data, we've got a library, and we've got music. See here, I've started to infer multiple kinds of data. I'm inferring that music are the big files, and they're probably stored in a directory. I knew that, and so I was able to make that inference pretty reliably. But I also knew there was an iTunes library, and I've played around with iTunes enough, and maybe some of you have, to know that there are various libraries you can maintain. So there's two data stores that I'm positing at this point. As I learn, by the way, more, I may find that there's more than this. Classification example here is the size by comparison screen. Here we have an input, an output, slow down a second. We have an input here, which are the comparisons being made. The user moves these sliders back and forth. And as those sliders move back and forth, we're updating comparisons. And that's a bit of internal data we're updating. However, when the user moves these back and forth, we also have an output. And this could be argued by some, but I know based upon the business requirements that this output is substantial and is derived. And so they're two separate things in my mind. I've broken, and also I believe from the business requirements side, I've broken up input and output. Down here, we have an output. This output is not something you can see from this dialog. The output is something that you have to investigate the requirements more to know about. Here's the output here. And that output is enabled by clicking hide or show comparison grid and also consistency. The point of these buttons is that they're not the functions, not at all. They're navigation buttons. Same up here with input for comparison notes, input for properties. You don't see the actual input here. You see navigation buttons that actually provide access to the inputs. Inquiry here. So I have an input here that I move the slider bar back and forth. I have an output that's produced when I move the slider bar back and forth. However, I also have an inquiry. Now, what is this inquiry? This inquiry is showing the two items being compared and the comparisons being made in the center. There's nothing derived occurring here. It's just providing information back from the database. So I have all these functions in this one dialog, and I'm maintaining two different kinds of data. I have comparisons and items. All right, here is a simpler example, which only has a single dialog, and this dialog actually has a single function. So this is a classical function point counting example where you have a single dialog, which is a single function, which frequently is not the case. And it is rarely the case in my examples, but in this case it is. We have data being shown here from a data store an external data store, and simply being shown. No processing occurring except what is necessary to display this information, but that is much more trivial than an output of the same magnitude might be. And so this is just an inquiry. This is the full screen of the application I've been showing you. The original screen here has many things happening here. You have an inquiry. This inquiry is showing information that is provided from an internal data store, items database, and it's not deriving it at all. You then have an input here, and again, I'm inferring this from this screen. The input is this Add Item button. Now, nothing is obvious from this Add Item button, but I'm able to infer from the requirements again that there is an input there. And then some other inputs here. The output is right here. I said before we had to reboot this section that this was an output because of derived information here. I still hold that true. However, there's sometimes a slight discrepancy or uncertainty between what's an output and what's an inquiry. And I might admit that that could be true here, that the output that's shown here could easily be an inquiry. Well, it could possibly be an inquiry. So sometimes there's a slight uncertainty. I tend to err, by the way, on the more complex side. So if I think something's an inquiry or an output, I'm not sure, I call it an output because, as you may know with coding, it always takes more work. So I always take the conservative approach. I didn't count everything on this screen. I just showed a few of the items here. We have all these menu items and everything. So there's plenty more to count here. I'm just trying to show a few examples. Now we're back finally to where we were, and I hope, Kelly, that the internet's working for us now with the sound. The app here is many screened. There's 5 screens. However, looking closely, just like apps that you may have traditionally, it has a wizard. And this wizard isn't complete until the user has entered everything and then hit register. It isn't complete when you click this button, automatic tracking enabled. It isn't complete when you set these times. It's complete only when you hit register. So we've got one input here to size out this input, and we'll do that sizing later. I'm going to give you a hint here. You consider all the fields the user modifies here. They all count. So it could be a bigger input, but it's just one input, one function, this entire thing. And then we have another function in this app. It's the output, and this occurs separately. And it has nothing to do with the wizard. So this app has an input and an output. That's it. At least that's all there is from the user perspective. It has 2 kinds of data, internal and what we call device reference. The device reference this is an Android app, and there's various things the device stores, and we're referring to that information. And we don't actually touch it, we just refer to it. And then there's information that we are modifying, for example, when we start, things like that. All right, so back to a rule that we went through before. I'm restating the rule here in a different way to try to emphasize it. You count functions only where the user requirement has been satisfied and there is nothing else to do. And so if the line in the requirements say the user will enter the data necessary to establish patient identification, it doesn't mean you enter a field called, it doesn't mean you're done when you enter a field called male as in gender. It doesn't mean you're done when you enter a field called age or name. You enter all those fields, and then you press the OK button or the commit button, and then you're done. The user requirements are satisfied then. That's the point where the system is waiting for more to happen. This is a point I've emphasized a few times because I've seen innumerable people trip up on what constitutes a function. All right, there's that Android app. It seems pretty confusing, laid out all over this screen, but I'll make it clearer to you all. The app is all the way here on the right, right, and the user, in this case, is the writer. We have a few different users. We have a administrator, perhaps, who watches things. We have another person who configures it, another person who sends alerts. I'll get into all this in a second, but the key here is that we've got the app, which I was sizing before, and the writer uses that. But behind the app, we have data collection occurring on a server. Behind data collection, we have another system that does mapping. So we're peeling back the layers, or rather, we've got an iceberg, and at the top of the iceberg, we see, above the water, we see the app. But below, we see all these additional things. Now, imagine that instead of one iceberg, we had bridges between the icebergs. Okay, that's these arrows. Maybe the analogy line goes so far, but you didn't need to develop the app and the data collection server together. They were developed separately. They communicate with each other. You didn't need to develop the data collection server with the mapping component. They were built separately, and they communicate with each other through a database that they share, actually. So this gets to the idea of what is the application boundary. Well, as you can see, I've decided that the application boundary here is each major component of the system. They're being built separately. If you were to count only that app that we counted on the previous screen, you'd have an input and an output, and that would not represent the entire system. I'm showing this screen first because I want to make this point clearer. If you count the app, you've got a few function points, but you don't count the data collection server with that, so you have to size that separately. And there's a ton of interaction occurring outside of this application boundary, the app boundary, outside the data collection server boundary, outside the mapping boundary. I'm going to go back 2 slides. That's what you count. The app has an output on the back end to the server. It has an input. It has an output, an input, and so on. They're paired. For every output you have on the app, you have an input on the data collection server, pretty much, and so on, and vice versa. And then you have additional things that occur in each app. So here you're counting faithfully with function point counting rules. You just have to recognize that there isn't necessarily one app that you're counting. There can be a system of different apps that are connected with each other that could have been done in parallel, even by the same team, but they're not one app. They're a system. Systems get counted at the individual component level, each of the apps going into the system. Then over here, we have an interesting case. I mentioned that in SEER, function-based sizing, we have something called an internal function. And I'm going to focus on that internal function for a second because we call it out. We actually count it. That is a special case of where the user doesn't see anything happening. Nothing is exiting the application boundary. It's rare, but it's our safety valve function that we use in SEER function-based sizing because it does occur sometimes, and users do need to count it, particularly our customers who are doing algorithmically intense work. There's internal data, and then there's pre-processing that processes this internal data. The action here occurs using what's called a cron job, for those of you who know what that is. That cron job is run fairly independently, and it processes the data, and nothing exits or enters the application boundary. That is an internal function right there. moving forward. To reemphasize the point, here's a lovely tali plate, and the chef makes each of these dishes, or maybe different chefs make each of these wonderful dishes. They all deserve to be considered separately. This is a system. This is, in cases, is a lunch system. But it's a system nonetheless, and each of these dishes are the applications. Another classification example. I chose this example because it has many more inputs, and I've seen user screens that had tons and tons of inputs, and it gets to the idea of scale. This is a relatively simple input screen, but it has a lot of inputs. I didn't count them, but I think the number is probably 15 or so. And then on this very screen, it has outputs. Hit compute, and you get this information below. Hit export to Excel, and you go somewhere else. So 2 outputs, 1 input. And also what I call here layer data. That's my information that's processed and that's updated based upon the inputs here. Here we have an entry screen, simple entry screen. Once you enter the the username and the password, specify a language, no internal data is updated. It just checks the passwords file. If the passwords file matches the inputs, then the user is permitted access. No internal data is updated. So it's just an inquiry. In this case, though, we actually look at 2 files. We look at the passwords file, and also we use language translations, which are maintained in the languages file. Here's an output. Best I can tell, since unfortunately I don't speak Danish, this is an output without any additional things occurring with it. So you specify location and various other information, and you hit a button, and you get an output. And it all operates together. There's derivation occurring that makes it an output. I know enough about this app to know that there is some derivation of internal data occurring. However, all the inputs are there to satisfy the output. Okay, this classification example is I wanted to show different types of sizing methods, and so this example shows using use case, inquiries, and inputs. Operator optimizes the bus plan. They actually have to provide inputs. Then they load the bus plan. Those are inquiries. And the customer gets the bus schedule out. That's another inquiry, bus plan. I've been told I'm going a little slowly, so I'm going to pick up the pace a bit because we had to go back a bit. So I'm going to go a little faster, but hopefully keep things clear. This classification example is another screen that has a ton happening on it, and each of these things happen separately. Record start stop, specify frame rate, specify process output, input source. I do each one of these things and I'm done. The system continues on. But the output here has a lot of derivation of information using the sound file, and so each of these are separate. In this example, it's an admin console for a web server. There's a ton of inputs and inquiries. I haven't called out each one, but you can see from all the navigational elements in the menu at the left that there are a ton of inputs and inquiries that the user accesses. And this is one particular screen, which is an inquiry. The server settings is the single file that I know is maintained. There may be more, but I haven't really mapped out which those are. This example looks a little bit like the iTunes example. It's slightly different. There is inputs. This is an input screen here. And then this here is largely just an inquiry screen because I'm getting information that's stored back. I can't modify this information anyway. I do the modification here. Then I have an inquiry screen, inquiry function on the left side here, which is getting just a list of the music files, or the directories rather in this case. This example has an input, and here I actually took into account the external input from a sound source, and it's a single input. The screen doesn't show it, the screen hints at it, and it hinted enough for me to know that there would be a sound source, and then that sound source goes into a recording file, which is maintained by this application. There's other things on this screen. I just wanted to make the point that your input can be coming from an outside the application boundary, but not necessarily something that the user could visually see, in this case the sound source. In this example, I have a bunch of inquiries. Looks like a complicated dialog. It's the Ubuntu software installation dialog. It's really just a bunch of inquiries. There's an inquiry to find software. There's inquiries to get more information. There's inquiries to navigate. It's all inquiries. But look at all the things that get modified, all the data that it relies on: the installed software, available software, installation configuration files. So a screen with a lot of inquiries. I chose this example to show internal functions in action. This is a defrag screen, disk defragmentation screen, and there's obviously an output here. The output shows the sectors that are getting defragmented, and then, or the clusters rather, and then the progress through the defragmentation. Well, this is a great output, and it's got a lot of colors, and I'm sure it took some work, but what's happening? What's happening is not on this screen. What's happening is the defragmentation itself, which is an internal function, not captured in this screen, but fairly obvious from the business requirements. You can't produce this report without something occurring underneath. That is the internal function. Rare, but it happens. In this classification, we have a bunch of outputs. The other one, we had a bunch of inquiries. In this case, we have a bunch of outputs, where information is being processed, summarized in this case, and summarized here, summarized in these screens in derivative ways, and outputs are being made. Now, this case here shows duplication. Duplication in that what happens up here in the device organizers portion of this output, of this screen, is different. Well, it's the same sort of thing that's happening down here in system organizers. However, they're different. They're two separate areas. You could argue that this is one output, but let's say that these are separate outputs. Well, if they're separate outputs, why not count them separately? The deal is that these are trivially repeated. They're outputs that needed to be developed once, but they're trivial instances of the same type of output, which is another rule in function point counting, that you don't count things more than once. You count unique functionality. In this example, another app, an equation solver, we have an inquiry and an output, and inside we have the equation. This example is interesting because you have a series of inputs here, and on the same screen you have an output. Why did I choose to call this an inquiry, and why did I choose to call this an output? For the same reason that this has substantial derivation, and this here above is modifying internal data. It could be argued that these were all part of the same thing, these inquiries and the output. However, these do modify, and this does provide an output that's in some ways much more than an inquiry. So I judged that these were an inquiry and an output separately. Inside, the data that's being stored is the equation itself, which is not persistent in the sense that when you close the app, it's gone. However, the equation is persistent enough when the app is open that there is an equation being maintained inside. Back to scoping. I've been hinting that some things are bigger or smaller than others, but not being very formal about it. And now we're going to introduce a little bit of formality. How do you gauge scope? Well, you figure out how many items there are in a function. You can call those inputs in a dialog. You can call those fields in a dialog or in a database. Those are the specific entries in a function, the entries that a user makes before they press the OK button, or however else input is accepted into the system. And then you categorize those. There are logical ways of categorizing all the inputs on a screen. For example, in the mapping application I showed before, there was longitude and latitude. That would be one category of items. And then there was other information that had to do with where you were in the sky, I think. That would be another category of items. We'll show you some of these categories in practice in slides to come. Depending upon how many categories and how many items you've got, you're rating your function low, average, or high complexity. They're integrated together so that you can have a lot of categories, but if you have relatively few items, you're not big. Or you can have relatively few categories, but if you have a lot of items, you're getting bigger or more complex is the terminology. Here's the actual complexity table that we use in function point counting. There's actually two tables. One is for transactions. Inputs, inquiries, and outputs have substantially the same numbers of things touched or numbers of fields in order to be rated simple, average, or complex. The data, internal, external data, share the same table. A little explanation is in order here. When I talk about logical files touched here, I'm talking about that logical data that we've been calling out throughout the presentation. If I have an input that relies on 3 tables, then it goes on to this row here. If I have an inquiry that relies on a single set of data, obviously it goes on the first row here. And then once I'm on that row, I say, well, how many fields have I worked on? If I have a lot of fields that I've worked on, but relatively few data, I could be average complexity because it gives me credit for more fields. If I have a lot of data that I'm accessing, but very few fields, well, it's still a bunch of work to integrate with all that data. I could be at least average complexity. The data, as in internal, external data, is evaluated based upon how many data groupings you've got and how many fields. Data groupings are like categories, logical ways of organizing fields together. So if I have a bunch of fields, but they're all very, very similar, then that's simple. The complexity ratings are almost misnomers, but not quite. Because if you have an input and it's of very high complexity or very low complexity, that just talks about that sort of input. One input screen can be compared to another input screen, and they may have equal complexity, but one input screen may be much more difficult to do because of the type of application that it is. The same can be true of outputs. You can have simple outputs or inquiries. You could have a simple output and a complex inquiry according to the rating scale. However, the output can take a lot more work to do. I emphasize that here. In these two examples, from the curricula of today, you see two outputs. One output is a simple set of code that outputs to the standard out to the user interface. It prints output from, and that's it. very simple to write these few lines of code in Java. The other output here may be of equal complexity in terms of the number of fields involved, but it was far more difficult to write. It was written bespoke. It wasn't actually a component. It was done by hand, this work. So it would be much more difficult to do. That's why we obviously produce a software estimation model for a reason. Once you enter your functional size, you may establish that these are two items of equivalent size, but it's all the other parameters in CRSM that say that this is much more work to do. That's why functional sizing complexities need to then be input into some sort of estimation method. The complexities alone don't tell you how much time a function takes to do. Now a few sizing examples. So we've established the idea of sizing and how when you count various fields, you get bigger complexities. These examples bring it to life. So we're just going to look at the input in this example. You know there are a bunch of other functions on this screen from before, but just the input. Logical files touched, 1, the WVS. Number of fields, I counted them ahead of time, 10. Complexity, according to the matrix, low. Next example, logical files touched, 1. Number of fields, here is an interesting thing, just two fields. This is a field, and these are one field, 2 fields, low complexity. Here we have 2 data items touched, comparisons and items. We're just looking at the output example here. 3 fields, this one, this one, this one, low complexity. 2 databases, 3 fields, two sets of logical data, I should say, low. Now we have some complexity. We're getting to average. Why average? 2 files touched, 2 logical files touched, and fields probably less than 7, but that gets us into average ratings, average complexity. We didn't even look at the internal function, which would be a different function entirely, which would add to the scope of the project. This output here touches just the events file. Fields, I believe there's 3. Even if there were more fields, it wouldn't move me from my assessment of low complexity because we have to have above a certain number of fields. Function point size and complexity, some people obsess about complexity. Honestly, if you're within a certain number of fields, you're fine. Calling something low, average, or high. You don't have to sweat about whether something has 19 or 20 fields. Choose high or choose average depending upon the other factors that are present. If it looks like an average and it has 19 fields, it's probably an average. If it looks complex and it has 19, then just make the jump into high complexity. There's a point that I made before about this very screen. I want to reemphasize that point here. You don't get extra credit when you trivially repeat a function. If you have an output that's repeated ad nauseum on a screen, and there were some examples previously, you may have noticed there were no boxes on things that were repeated. That's because it doesn't take a lot of effort to repeat those items. You count functions once only, the first time they're uniquely deployed. Here we have that code example again. Logical files touched? None. Nothing touched in this case. Output, yes, we do output a field. It's a command, it's a string that's output to the user interface, low complexity. Here we have a wonderful example of a huge screen, that patient example where we have many logical files touched. This is a complicated hospital record system. I haven't even gotten to the number of files here. I kind of gave up at 3 files, but I know there are more. And fields, I counted at least 55. So without a second glance, I know this screen has high complexity. And by the way, this is this screen only. There's a bunch of tabs here. Those are all separate functions probably. Now we've counted all along all the transactional data, and the internal and external data have been used to support our counting the transactional data, but these also get counted, internal and external data. I was going into the complexity of data before, and I glossed over how you categorize the complexity of the data. The truth is that data often resembles tables, and it's a fair way to start by saying the way you categorize things into tables is basically the logical categories. So that matrix had categories and it had fields. And the more fields you have, the more complex the logical data is. The more categories that the fields are put into, the more complex it is. In this case, I think it's pretty easy to count the fields. Count all the fields in this table, this, add them up. That's the number of fields. The tricky part is figuring out how many categories the fields go into. Well, in this schema here, the work has pretty much been done for us. There's a category called employees, orders, shippers, customers, etc. Now, these categories aren't always the way fields are categorized from the user perspective, but in this case, it's a fair bet that they are categorized from this perspective. So we'd have many fields, whatever that number is, and divided into 8 categories. 8 categories would land us, in this case, into a complex set of logical data. User requirements are very important, and having a full set of requirements are very important. I made the mistake initially of thinking this was a simple application, but I looked it up, and I got addicted to it as well, playing it, and I found out that there was much more to this application than met the eye. I really needed to know all the requirements to count this. That one screen was the tip of the iceberg. These were all the screens involved in that one application. So you have to make sure that you have all the documents available to do a complete sizing. Those would be some of the items mentioned here. These are the most common items that we use. The wireframe or the mock-up is very important, obviously, but also the use cases, interviewing users, all the usual suspects are what play a role in doing a functional count, and of course the requirements as well. I'm almost done, but I would be remiss if I didn't bring up Cosmic, the other leading functional sizing method, because it is itself a very good metric. It's what's called in some ways a second generation measure because it came along after function points, but both are in very common use. Function points have the perspective of functions of various sizes, the apples and oranges, quote unquote, of various types of functions and their differing complexities represented in an abstract way with these circles. Cosmic looks at things differently. Cosmic looks at things in terms of data entering and exiting the application interface. That's it. There aren't inputs, outputs like that. There are basically entries and exits. Here's an example of Cosmic. There are 3 examples here, actually, showing how you count when data enters and when data exits the application boundary, when a read is made from persistent storage and a write is made from persistent storage. And these all show similar concepts, the same concept in different perspectives. Entry, exit. Entry, read, write. Cosmic was intended to address the idea of different application boundaries, maybe layers of systems interacting with each other, like the example that I showed. And it does handle that particularly well, although function points can also be adapted to that, as I showed. Now, the last step in doing a functional count is adding the information up into a unified count. So let's say that I have a dialog that is, a bunch of inputs, inquiries, outputs, etc. Those are not something that I can enter into any sort of estimation method, or that I can use, as a cardinal measure to compare one system to another. I can't say this, or it would be inefficient to say this application has 2 outputs, 3 inquiries, etc., and this other application has these outputs, inquiries, etc., these number. It wouldn't be comparable. I need a single combined figure to compare the two, or it'd be better off with a single combined figure. It'd be easier to say, for example, this application is 200 function points, 200 unadjusted function points, and this other application is 300. That would be much more comparable. And here's an example of how you do that. I'm not going to go into great detail here, but I will show you how it is basically done. In CRSEM, you enter the functions and all the calculations are done for the user behind the scenes. But this example makes it more explicit. I have in an application a count of the inquiries, inputs, outputs, etc., all the various functions. I then categorize them in terms of their complexity, average, low, etc. There are no high ones here, but there could have been. The next thing that I do is I look at the values. We didn't show you the values, but given low, average, or high complexity for a function, there's a number associated with that. I think it's, for example, 3 for low, 5 for average, and 7 for high. For one of the transactional function points, they're slightly different depending upon whether it's an input, inquiry, or output. Here are the actual numbers. So for transactions, we have low, average, or high complexity being translated into these numbers. For data, we have low, average, or high complexity being translated into these numbers. Inquiry, average, 4. External data, average, 7. So now we've translated all these functions with all these different complexities into a set of numbers, and numbers allow us to add it up. And here we have the size of our application, in this case 38 unadjusted function points. Unadjusted is a historical legacy. There were previously adjustment factors applied to function points, but they have largely fallen out of favor. Now you enter the unadjusted function point into a model, and the model, such as CRSEM, produces the estimate. They're called unadjusted function points, but they're never really adjusted, except within the model itself. In CRSEM, I'd be remiss if I didn't show you the function-based sizing screen. You can see the strong resemblance between what I've been showing you today and how CRSEM works. External inputs are the inputs, the outputs, the inquiries. These are IFBUG standard terminology, which we do honor. External interface files is external data, internal data. But in function-based sizing, we break things down further to make it easier for users who don't do this every day to enter function point sizes. So these examples were, these are common examples of outputs, and we let the user enter these entries at this lower level, and then they're summed into outputs, inputs, etc. And then there's that internal function at the bottom. Rarely used, but when you need it, it's there. Cosmic function points are also supported. And here's an example of entries using cosmic function points. These are parameters in CRSEM. And I've just taken snapshots to show you them. All right, this has been a long presentation, and I hope you've all gotten a ton out of this. I've had a lot of fun preparing it for you guys.